Good day, everyone. Thank you for attending today's Foxconn Quantum Computing Seminar. Today, we have the pleasure of having Asad Raza to give us a talk on online learning of quantum processes. So Asad is going to start his PhD at the University of Chicago with Bill Feveran. He finished his master's in Berlin, co-supervised by Jens Eisert and Alex Grillo. Before that, he had his undergraduate in computing mathematics at the City University of Hong Kong, advised by Oscar Dalston. And his interest is mainly on questions surrounding quantum computation and complexity theory. So Asad, the floor is yours.
Thank you, Jeno. And thanks for the invitation. As you pointed out, I'll be talking about something that's called online learning of quantum processes. I'll explain what this is. Before that, I want to highlight that this is joint work with Matthias Caro, Jens Eisert, and Sumit Khatri, who were my colleagues at FU Berlin. So let's start. This is a ChatGPT rendering of a scientist trying to understand a quantum system, right? But when you talk about understanding or learning about a quantum system, what does that even mean? The learning can broadly refer to the fact that you might care about learning the ground state or the energy or properties thereof of those special states, or testing a property of a quantum system as a whole, right? But again, if I kind of just have a very high-level view and philosophically ask, what does it mean to learn a quantum state, right? There, you can start with a simple answer and say that, well, learning would just mean learning everything there is, and then when you're in the testing phase, you can basically answer every question there is that pops up, right? That would mean that you kind of make lots and lots of measurements, like we have in pink here, and do what's called full state tomography. For that, you need well, many copies of the state, and you keep performing measurements, entangled or not. But roughly, if you do that, then your complexity, by complexity I mean the number of copies of the state, which is k here, scales like d squared, where d is 2 to the n conventionally, and that is scaling exponentially in the number of qubits. So while this is great in the sense that you learn the state in trace distance, the con, however, is that the cost is very high, right? And you might have to perform entangling measurements. And so this is a cartoon that kind of summarizes the situation. So let's say that there's this learner that learned the full state and then asks, now what? And then they go to a physicist and ask, okay, now what? The physicist tells them that, okay, now tell me the expectation values of these few observables that I care about. And then the learner becomes this, scratches her hair, goes bald, and says, why did I even learn the full state? Right? Because if at the end of the day you care about predicting expectation values of very few observables, then learning the full state seems a bit wasteful. And this is precisely the motivation behind. This was the motivation behind Aaronson's notion of pretty good learning of quantum states, or that's also called packed learning of quantum states, that I'll come to in a moment. What is asked for is that, let's say that rho right here is an unknown quantum state, and you have to learn some state sigma such that the trace expectation values are close in absolute value distance for particular EIs, right? And in packed learning, probably approximately correct learning, you have some distribution assumptions such that the E's, where E's are your binary POVM elements or the effect operators, they come from some unknown distribution D. And then what Aaronson guarantees is that as long as you sample E's IID from this unknown distribution, then you will need something like n over epsilon squared many sort of training data set. And that's amazing, because what's happening here is that previously you needed something like exponential in n many copies of the state to learn the full state. But here, if you relax the notion of learning, you're exponentially better in terms of quote unquote sample complexity, right? But of course, like with anything, one can point out that there's a problem here, which is that this IID assumption might be just too strong, right? And it's just not always possible to sample things IID from these distributions, and nature might be a bit more complicated than that. For that, Aronson fixed his own problem in 2017, where he introduced shadow tomography, right? And in shadow tomography, he fixed this IID problem by essentially replacing the POVM elements by by going beyond the IID model, in the sense that the POVM elements are not sampled IID, but now they have to be any POVM elements, except that they're just known in advance. And that's already a lot of progress. And for that, you still need exponentially fewer copies of the state, which is basically which is log of m, which is already very nice, and it's log of the dimension as well. So that's already pretty good. And this was the statement of shadow tomography, that given any d-dimensional unknown quantum state, as well as known two outcome measurements. Now, if I just zoom in on the known aspect, one can still again sort of ask a further question that, well, it's great that you could go beyond IID, but maybe this assumption of having all of the POVM elements known in advance could still be a bit strong, right? And so again, to fix that problem, Aronson and collaborators introduced this completely adversarial model in which the measurements are not known. They're adaptive, even adversarial, right? And so this was called online learning of quantum states. Well, there, what is happening is that, let's say that you have an unknown quantum state rho. You're supposed to produce sigma that has expectation value close in absolute distance for adversarial EIs, right? So the setting is the same, or what we're changing is just the fact that the EIs are now adversarial. There is no distribution assumptions at all, right? But now you cannot. But now the difference here is that previously we were supposed to produce epsilon close expectation values on all of the EIs, but here the model is that on some of the EIs you can be epsilon far away, which we call a mistake, right? So the cost of having EIs to be adversarial is that you might have to make like some mistakes on some of the EIs, which is sort of the compromise we're trying to make here. And what Aronson guaranteed, Aronson, Chen, Hazan, Kale, and Nayak in 2019, they gave a strategy that guarantees that these mistakes, where you're epsilon far from they're not too many actually. They're only scaling like n over epsilon squared, right? So let's say that if you have sub-exponentially many EIs, you're only sort of wrong on polynomially many EIs, which is still a pretty strong guarantee, given that it works for any unknown quantum state. And the EIs are completely not just adaptive, but adversarial. So, well, this seems like very computer sciencey, and what is the point of going too rigorous on the adversarial setting? Well, for one, it found very nice application in the adaptive version of shadow tomography. So beforehand, I showed how Aronson came up with the original shadow tomography in 2017, where these EIs were supposed to be known. But in 2023, Badescu and Donald basically used this online learning framework to get what I think are still the best known bounds for adaptive version of shadow tomography, which is that these EIs need not to be known in advance. They could be completely adversarial. And shadow tomography, as we know, is used in multiple applications these days. So now, just to recap the flavors of learning, firstly, we have this full tomography, right, where you learn the state in trace distance, you learn everything, but the sample complexity is very high. Then Aronson introduced this pack learning of quantum states, where you only care about predicting the expectation values of some IID POVM elements. The problem there was that this IID assumption might have been too strong for that. He introduced shadow tomography, where you could go beyond the IID assumption, but the EIs had to be known in advance and were not adaptive. To fix the non-adaptive problem, Ernst, Chen, Azan, Kale, and Nayak came up with online learning, where EIs were completely adversarial, no assumptions whatsoever, no assumption on the unknown state whatsoever. On the other hand, they introduced this notion of a mistake where you were wrong on certain EIs, and they ensured that these mistakes were not too many. And finally, this online learning came full circle that by basically robustifying shadow tomography and making it adaptive. So that's great. The state picture is very neat, and the threads tied together. But what if I ask the same question about channels, right? And there, this is basically an excerpt from Aronson's 2007 paper, where he introduced this packed learning quantum states, where he says that one might hope for a far-reaching generalization of our learning theorem to what is known as quantum process tomography. Here, the goal is to learn an quantum operation on n qubits by feeding it inputs and examining the outputs. But for process tomography, it is not hard to show that exponentially many measurements are indeed needed. In other words, the analog of our learning theorem is false. Still, it will be interesting to know if there's anything to say about pretty good process tomography for restricted classes of operations. So basically, pretty good process tomography in the sense of packed learning is still hard for channels. And I think people in the audience do have results about this as well for general channels. And so what Aronson kind of puts forward is that, can you still say something about pretty good process tomography of some restricted classes of quantum channels? And so the setting would be as follows, right? So you have an input quantum state that goes to some unknown process that is shown here in blue, and that process gives you n of rho, where n is a quantum channel that is unknown, and you have to predict a trace of m, where m is a measurement or a binary POVM element that is measured on the output that comes out of the channel, right? And one, of course, can generalize this where you have channels with memories, so on and so forth. And so that was the setting. But again, one can ask the question that why do we need to do this? And the motivations are roughly the same as we had for states, right? So we want to learn, properties of now a bit more general quantum systems in a query efficient way, and queries in quotes, because I'll explain what query means in this particular setting. And of course, just like we have useful applications of online learning in shadow tomography protocols, can we have something similar for channels? That would be super exciting. And then as Aronson already pointed out, that online learning of general channels is hard. Can we learn special classes of quantum processes? And here, spoiler alert, we will be focusing on Pauli channels and show that they are online learnable. And focusing on them is also interesting because they form they're pretty much everywhere in quantum information, notably in quantum error correction as noise models. So now I would try to try to explain a bit more in detail how this online learning setup is working, firstly for states, and then I will generalize that for channels. And so before that, if there's any questions on the recap, on the background that I just gave, I'd be happy to take them now, or we can just take the questions later or whatever. Okay, so
okay, I don't know if I wanted to ask it now or later, but maybe now. In the setting where you have the adversarial case, so you allow mistakes, right? I was just curious, would you know which EIs is likely wrong? Or this is not known?
That's a great question. You don't know. You don't know in advance. I think that is what online learning is guaranteeing you is that you're wrong on at most poly many EIs, but where those mistakes are happening is actually something that I don't think you can. At least these papers don't guarantee these.
Okay.
Maybe you can do that, but these papers in the quantum literature do not guarantee that. But that's an interesting question, actually.
Right. Okay. Yeah, that's it. Thank you.
Cool. All right. So now let's just understand a bit more deeply what is happening in online learning of quantum states. So here's the setup. There's an adversary shown here in red, and then there's a learner shown here with the school bag. So now the adversary is giving MT. So MT are now sorry for the change of notation, MT is now a measurement or a binary POVM element. So I'll be using these two terms interchangeably. So now what happens is that the adversary gives a POVM element to the learner and asks for the trace expectation of that measurement with respect to an unknown state. But then the unknown state is actually rho star. And then so since the learner does not know what rho star is, the learner basically comes up with rho t, where t just denotes a time step. So here t equals 1, where time step is equal to 1. So at the first time step, the learner actually does not know anything about the unknown state. So maybe at rho t equals 1, that state is just a maximum mixed state. And the learner returns the expectation value to the adversary. The adversary, on the other hand, calculates the exact or the epsilon close expectation value with respect to the actual true state rho star, and tells the learner that, okay, this was supposed to be, your expectation value instead of what you gave me. And then the learner learns, the learner receives feedback. And this keeps on going for a capital T time steps between the learner and the adversary. The learner gives their own estimate of the expectation value, and the adversary gives returns feedback with respect to the correct state rho star. And at each time step, the learner kind of suffers a loss. So this is how you quantify loss, which is very natural. That is what is the difference, the absolute difference between the learner's prediction, which is on the left here, and the adversary's prediction, which is the second summit. Sorry, the adversary's feedback, which is the second summit. And that is the learner's loss at time step t. Right? And like I've been alluding before, a mistake is just defined wherever the loss is more than epsilon. And the goal in this entire setup of online learning of quantum states is to just minimize the number of mistakes that you make. The strategy for that, so firstly, the goal is to minimize mistakes. Another very related metric that we will be using to kind of minimize these mistakes or upper bound these mistakes is through something called regret. And regret is defined as follows. It's also intuitive enough, in the sense that the first summand here is basically kind of, let's say that you interact with the adversary for capital T time steps. So the left summand is basically quantifying the total loss over T time steps for the learner, right? And the second summand is quantifying what could have been the minimum possible loss in hindsight. And so the regret as a whole is basically telling you how far were you from the optimal sort of prediction. So how much more loss did you incur compared to the optimal sort of loss that could have been incurred throughout these T time steps. And again, like I alluded to before, Aronson, Chen, Hazan, Naik guaranteed that there exists a strategy such that you never make more than n over epsilon squared many mistakes for any rho star. This is great. What you can see is that this result is kind of a result for arbitrary quantum states. And well, to put it another way, it's a result for any state preparation channel, right? Because the state preparation channel is just a kind of boring channel where you input a complex number and get out a state up to a phase, and that gives you the same state over and over. And so the question is that can we go beyond, right? Can we go beyond to more interesting classes of channels? And so for that, we need to define the setting of online learning quantum channels to begin with, right? So here now you're not just given a measurement, but you're given a tuple where you have a state and a measurement. And so what the learner wants to now has to do is to predict the following quantity, which is the expectation value with respect to the measurement, but now on the state with respect to a state that comes out of the unknown channel, right? So NT is the learner's estimate right here of the unknown channel. And then the adversary again provides feedback with respect to the actual channel that is completely unknown to the learner, which is n star. And the interactions go on for capital T time steps, like before. The losses are quantified in exactly the same way as was the case with the states. And again, you define the mistake in exactly the same way where the loss is greater than epsilon. And again, regret is again defined in completely analogous way. So this will be the setting throughout our talk. So if there's any questions about this, I would encourage you speak up now.
So, sorry, I just want to clarify. So the purpose is to abandoning the channel, so that so the n is unknown. So you want to estimate it, but would that also depend on the input state law you use?
Sorry, could you repeat the question? I don't think I got it.
My question is that you are going to learn the channel, which is n,
Right.
But the law you put into the channel, will they also influence the result? Does it because you assume you don't know the input state law, right? Or you assume you know.
Right. So we do have we do know the input state row because now you're given this tuple, right? So you're not just given the measurement, but if you can see my pointer, you can see you have both the input state row and the measurement on the output state that you'll be performing, right? So you do have a complete classical description of row and a complete classical description of the measurement.
Okay, so this is given, and can law and m change from time to time?
Well, n is a fixed channel, right? So n is is an unknown channel but fixed.
But law and m can be changed, right?
So there's two channels. So nt can change from time to time because nt is learner's estimate of the channel, but n star is the actual channel that the learner wants to learn, and that will be fixed. That is a channel that only the adversary knows, and that is what the learner is trying to learn.
And how about law and mt?
Rho t and mt will be changing from time step to time step. So they're different at each time step.
I see. Okay.
That's
okay.
right.
Thank you. Yeah. Thank you.
And so to your earlier point about whether rho will influence how you learn the channel, I think yes. And despite that, the guarantee that we will give is pretty strong. We will tell you that for certain channels, no matter what measurements you choose, no matter what states you choose, you will not make more than, let's say, polynomially many mistakes. So that's the guarantee we'll talk about in a bit.
I see. Okay, thank you.
Yeah. Cool. So going ahead, you can also generalize the setting to higher order maps. I won't be talking about these in great detail, but just to give, just to kind of allude to how the setup is much more general. So for any sort of, let's say there's a channel with memory, and for that you can sort of define a tester that people in higher order maps sort of define, where you can say that the probability of being measuring I at the output is trace of EAB times the Choi matrix of this channel, and EAB is basically now very neatly encapsulating both the measurement and the state that we had actually, and this is very nice because previously you had to kind of write down both the state and the measurement, but now this is similar to the state setting where you have like this is the Choi matrix up to a normalization Choi state, and then this is sort of the measurement operator, so to speak, right? So this kind of nicely encapsulates both the state and the measurement. And one useful property that I'll be using throughout this talk is that this quantity that we cared about before with measurement here and the state here is now very nicely encapsulated, is very nicely equivalent actually to trace of EAB times the Choi matrix, and EAB is exactly the same here. So this is this can be readily verified. And now your regret doesn't have like the state, the channel, and the measurement. It just has dependence on two quantities, which is your EAB and the Choi matrix. Okay. Before I talk about learning specific classes of channels, there's an obvious idea that would pop into your mind when you try to learn quantum channels, right? And that is to use the Chern-Minkowski isomorphism. And there you just ask the question that why don't you just learn the choice state of the channel, and that should be it. Because and this is actually more to the point in this case, because you do have state learning guarantees from Aronson et al. Right? So why can't we just learn the choice state of the channel in a mistake with a bounded number of mistakes, like we've been talking about? But to see why that does not work, I'll see this. So firstly, we have loss defined as follows. So this is the loss that we care about, right? We have loss parameterized by EAB and the Choi matrix. And note that this is the Choi matrix that helped us create the equivalence between the channel learning setting. So this is not the Choi state, but the Choi matrix, which is unnormalized. And now L prime is not the derivative or anything. It's just notation for where you have losses defined with respect to the Choi state gamma. The Choi state gamma EB does have a normalization factor that is D. And so what Aronson et al. Give you is bounds on with respect to a normalized state, right? It's a state that is hence it's normalized. So the losses there are with respect to L prime. And so one can see that if you have regret that is on the level of Choi matrices, then even if Aronson et al. Give you very good regret bounds on the level of normalized states, which is L prime here, what you want to do is to learn in a much stricter setting, which is with respect to the Choi matrix, right? And that just directly blows up your regret bounds by a factor of D, right? So that naive or I'd say simple strategy does not work. Just because of this normalization conditions and that when you go to the channel picture, the correct metric to look at, the correct sort of loss to look at is with respect to the Choi matrices and not just the Choi states. And so with that said, firstly, we see that we kind of make Aronson's statement rigorous as to why channels in general are hard to learn. And here I would just show that not just arbitrary channels, even at arbitrary unitaries, you cannot do a lot very well. To see this, imagine that we were to learn a function that was as follows, where b was unknown, where there's a bit b, and there's a Boolean function that maps n bits to 1 bit, right? And here you're given inputs, and you want to predict what comes out in the output, right? So the adversary keeps giving you inputs, and you have to correctly guess what is there in the output register. And note that since the truth table of the function f is of length t to the n, then the adversary can sort of make you make to the n many mistakes, because at each time step, if the adversary chooses an independent x, then the probability of you guessing that correctly is essentially half and half. That is roughly the intuition, and that directly implies lower bound of to the n. And here is where I would recall this statement from the 2007 paper again, that says that it would be interesting to say anything about pretty good process tomography for restricted classes of operations. So how far can we restrict from unitaries? Turns out that we will be showing that you can avoid this exponential scaling for arbitrary Pauli channels, and as a matter of fact, any convex mixture of known channels, right? So mixed unitaries and so on and so forth. The second class of channels is channels with polynomial gate complexity. And the third class is basically any multi-time processes with the structure in 1 and 2, which is that either they have this Pauli structure or they're multi-time processes with sort of poly many steps, so to speak. Okay, cool. So now I'll be going into, now I'll be explaining how the proof for learning online learning arbitrary Pauli channels work. Recall that there's, you can always write a Pauli channel as follows, where PZXs are just, any n-qubit Paulis, and then this bold vector is just the Pauli array distribution, which is a valid probability distribution. So firstly, note that for any given Pauli channel, right, all that you do not know about this channel is a 4 to the n dimensional classical probability distribution, right? Because everything else, if you fix the lexicographical ordering, you know everything else about the channel. What you don't know is this is precisely this distribution. And of course, since it's a distribution, it's normalized, and it's important because we were talking previously about how Aaronson's result works for normalized iterates and not for Choi states that I was discussing, and not for Choi matrices. So that is why normalization is important in online learning algorithms. So that gives us two very concrete things to work with. Having said that, you can readily verify that you can write the Choi matrix of a Pauli channel, CAB, as follows, where PZX is again the Pauli array distribution, and gamma ABZX is just maximally entangled state conjugated by n-qubit Paulis on specific subsystems. So we'll just be using this structure. So note that what we had to predict was the following quantity, right? So now if I just substitute the form of CAB here, I'll just get the second equality. And if I just write down this trace EAB gamma ABZX, if I call this quantity M ZX, then what I have right here is that it's a dot product. This quantity at the rightmost side is a dot product between two real vectors, right? So it's a convex combination essentially, and you can see that M ZX has entries that are real and actually bounded between 0 and 1. So so now what we have is that the learner's predictions are just a convex combination of M ZXs, right? And so your regret now essentially is goes from trace of EAB CAB type things to just dot products between two vectors. And well, that is some simplification. And having written this or sort of quasi regret, in the sense, I'll explain what quasi is here, in this form will be helpful in the following slide. So now there's an algorithm that helps us bound this quasi regret if I do the following procedure. And what is that? And the procedure is rather simple. You start with sort of a uniform distribution over all the Paulis, or all the 4 to the n Paulis, and sort of initialize a probability distribution over all 4 to the n, many of them. And then when you receive an EAB from the adversary, you calculate this this MZX for every time step t. And given the value of this thing between 0 and 1, you kind of update your weight on that particular Pauli ZX for the next iteration. So you can think of the M ZX value as a sort of a loss, right? So if it's high, then your weight is low on that corresponding Pauli in the subsequent iteration, and vice versa. And if you do this, this algorithm, I think this is Aurora, Hazan, and Kale from 2012, guarantees that your predictions, the sum of your predictions, and the sum of the actual predictions are actually not too far. And that is actually something like eta times t plus n over eta. So n, remember that the support of this distribution is 4 to the n, and the regret is only log of that dimension, which is already something. And note that I can tune this learning rate to be eta. So if I take this eta to be 1 over square root of t, then I'm having regret that is sublinear, not linear, which would have been trivial. And once I have this guarantee, I can generalize this to regret with feedback, because note that this is just my prediction versus the actual prediction. There's no feedback coming from the adversary, and then there's this one-line argument that helps you kind of figure out that the same bound holds for mistakes. And how do you see that? You just note that for any number of rounds that you interact with the adversary, let's call T prime to be the number of rounds where you made a mistake, right? So going back to Jello's point, you don't know where you made a mistake, but you just know that let's say that there's capital T prime many time steps that are, of course, less than or equal to actually the total number of time steps, right? And so you have that the regret is greater than just the loss accumulated over those time steps, because the second summon is not there. That kind of subtracts things out, right? And by definition of a loss, you have loss that is lower bounded by epsilon. So you just have trivially T prime epsilon here, which is a lower bound, and the upper bound just kind of comes from the previous slide where you had this guarantee and you substitute eta to be epsilon over 4. By combining these two, you can just simplify and see that T prime is at most n over epsilon squared. So this was a bit involved, but the point here was to show that there's this algorithm that is multiplicative weights updates that you can tailor to Pauli channels and get a mistake bound at the end of the day that is exactly the same scaling wise to the bound that you have for states. So what you're doing is essentially lifting the bounds from online learning of states to online learning arbitrary Pauli channels. Okay, so before I move on, I think I'd be happy to take questions here, because we finished the proof of or the proof sketch of online learning of Pauli channels. Okay.
Okay, I just wanted to ask. Okay, I don't know how to even ask the question. Sort of like, where is it that this kind of lifting of the result from the state case to the channel, where is it exactly? Why sort of like the Pauli restriction is needed? Is it just because of the being able to write in terms of these vectors, which is not something you can do in general?
Yeah, exactly. So you're going in the right direction. I think that is roughly the idea, because I think having the Pauli structure helps you, because you do make this, like, you do know that you do know all the Paulis, right? All that you don't know is just the Pauli error rate distribution, right? And then when you sort of write this Choi matrix of a Pauli channel, let me just go to the corresponding slide first. It's easy to see. Right, exactly. So so since you know all the Paulis yourself, you basically know gamma ABZX, and you know EAB that was given to you by the adversary, right? But then for arbitrary channels, you will not know ABZX, because ABZX is conjugating a maximally mixed state by Paulis, right? And that you would not know in the general case. I think so this will also work for any mixed unitary channel, and like I said, this will exactly be the same for any convex combination of known channels, right? Because what we're exploiting here is the property that we don't know the convex combination or the distribution with respect to which the convex combination is taken. Right? But we do know the channels per se.
Okay, thanks.
Okay, so now having established that, there's multiple applications that you can cook up. So first, so remember that I gave in the motivation section for channel learning, I highlighted that it would be great to have shadow tomography procedures for Pauli channels, and here we have just that, right? Because having because sorry, now we'll show how using similar techniques you can have sort of quote unquote sample efficient shadow tomography of Pauli channels, and this is not hard to see because recall again that at the end of the day, what you want to predict is this quantity, and that you can write down as a product between two real vectors. So you can write this down as an expectation of mzx with respect to the unknown distribution p. And since you do know the classical description of m, again, this is computationally costly classically, but at the end of the day, you do know and you can calculate mzx elements for each zx, right? So what you're doing at the end of the day is that you can measure in the Bell basis, right? And when you measure the choice state of the channel in the Bell basis, then you can basically sample, in other words, from the Pauli error rate distribution right here, which is unknown, right? And when you make, let's say, x many independent measurements, then you have exactly those many samples that are given to you, IID from that distribution. And once you have that, what you're doing is basically predicting the expectation value of these things. And for that, you do remember that you have a sort of as many as you want independent outcomes from this distribution, right? Which is a number by as many as you want. I mean, as many measurements as you make, you'll have IID samples from this array distribution, and having that, you can just use adaptive data analysis to answer m adaptive queries given only sort of log m over epsilon cubed many samples, and exactly these many samples roughly. So that's very nice in the sense that you only sort of make log m many measurements and answer m many adaptive queries, right? So here what we're doing is just that we're writing the task of shadow tomography of Pauli channels in the language of adaptive data analysis, and just importing the bounds right away from the classical literature, and that's great. So for Pauli channels, this is amazing. This grows, as log of the dimension and log of the number of measurements that you make. That is amazing. But this only works for Pauli channels, and for arbitrary channels, this kind of grows like the bound kind of blows up blows up as the diamond norm between your channel and the Pauli toral bound blows up as Pauli toral version of the unknown channel, and sorry, let me recall this correctly. Yes, okay, yeah. It's right here. So it blows up as the actual channel and its Pauli toral version, right? And this could in general blow up your bounds. So this does not work for as efficiently for arbitrary channels, but of course, Pauli toral version of Pauli channels is the same thing. Then you basically just don't have this cost right there. So the second class of channels that we give guarantees for is channels with bounded gate complexity. And given that we are sort of getting towards the end of the talk, I will just quickly go through this part, and in case there's any questions, we can answer these towards the end of the talk. And here we give the guarantee that is as follows: that any gate G channel. So now I imagine that the channel is written as a quantum circuit, such that this quantum channel is made of like 3-qubit smaller channels, such that these 3-qubit smaller channels are polynomially many. And as long as that condition is fulfilled, there's this guarantee that you will never make G log Gn over epsilon squared many mistakes. So there's a factor of G. This is a bit different from the Pauli channel bound that we have. And the way we do this is through something called a Dudley's integral that takes the following form for any function ft. Here, NT is something called a sequential covering number. We know that sequential covering number for CPTP maps and qubit CPTP maps of gauge G in diamond norm is growing as follows. And so the proof strategy is to bound something of this form that it can easily do by using Euler's inequality and properties of norms to show equation 3.11 and then just substituting essentially the known bounds on this right hand side to then evaluate this integral. This is, I know I'm going a bit fast here, but again, please do ask questions during towards the end. Right. So at the end of the day, once you perform this integral, you get something like L is L Tg log Gn, where L is Lipschitz constant. You can take this to be 1, and that kind of so this is the regret bound, and then you can translate that to the mistake bound of that's stated above. Right. This section will basically show that now the upper bounds that we have are essentially optimal. And so, remember that for Pauli channels, we gave a mistake bound that was scaling as n over epsilon squared. And so here you give almost a matching lower bound. And so to see that, let's consider this picture where you have an unknown channel that has a Pauli Z somewhere. You just don't know which qubit index is the Pauli Z acting on. And now imagine that the adversary gives you for the measurements and for the input states the same things, which are like this, which are zeros plus somewhere and then zeros again. Now note that the trace of ET and rho will be 0 in case the adversary, in case the learner correctly guesses the qubit index, right? Because then the Z will basically flip plus to a minus, right? And then these two things will be orthogonal, hence you'll have trace values of 0, and otherwise it'll be 1. But how can the adversary now make the learner make at least n many mistakes? What the adversary does is that, well, the adversary can just be dishonest at a given time step, right? So whatever the learner says, predicts 0, the adversary claims 1, and vice versa. And the adversary can do that because at the nth time step, the adversary can just claim that there is a channel that is consistent with the adversary's feedback by just locating the Z at the very last qubit index, hence forcing the learner to make at least n many mistakes. A similar strategy can be employed to show that you indeed have to be computationally inefficient to learn these Pauli channels. So note that while we are efficient in the number of mistakes, we are very inefficient computationally. Why? Because if you remember that matrix multiplicative weights updates, we were basically kind of updating a vector that is exponentially long, particularly that is a vector of length 4 to the n, right? And when you update that, it takes an exponential amount of time. And so what we show here is that for Pauli channels, this is actually the best you can do. And the strategy that I kind of highlight here is very simple. It's very simple to see in the following sense, right? So consider the following proof strategy, right? So let's say that the learner's output, let's just play like a simple game where the expectation values are either 1 or 0, right? And xt is the output of from the learner, and the adversary will always contradict the output of the learner by just having not xt, right? So if the learner claims 0, the adversary claims 1, and vice versa. The input vector m, right, that is kind of encapsulating the input state and the output p of m in this vector is always going to be 0, 0, 0. So in the sense that the EAB is always just trivially 0. And why does that work? And why is the adversary allowed to do such a thing? Because all you have to show is that there is a probability distribution that is consistent with adversary's feedback. In particular, the adversary's feedback, which was not xt, is consistent with some distribution p star nt. And so when the adversary has to come out clean to the learner by contradicting all their outputs, the adversary can just fix 0 entries on the vectors of zero entries on the entries of m that the learner saw, right? And just fix the non-zero entry to non-zero entry towards the entry of m that the learner never saw. And that is always possible because the learner is polytime and you have only polymany interactions. So of course, their entries the learner will never see, and the adversary, being computationally unbounded, knows which entries the learner see. And so the adversary can just sort of retroactively cheat. Okay. Apart from that, we before going on to multi-time processes, so here we kind of are claiming what one might call a trivial lower bound, in the sense that to even read the input you have to expend exponentially exponential effort, and so there's no chance that you can learn this computationally efficiently. Well, that's fair criticism, but also note that this proof kind of shows that, or the rigorous version thereof shows that there does not exist any strategy where you can look at just polymany entries and just online learn the Pauli channel, because the adversary, being adversarial, can always cheat retroactively. Moreover, we also show a much more non-trivial lower bound, in the sense where the inputs are only poly-sized, and assuming one-way functions, we show that assuming the existence of one-way functions, we do show that even in that case, learning sort of channels with bound gate complexity is already computationally hard. And that goes by sort of embedding a pseudo-random function into the learning problem. So that I won't sort of explaining in a great detail, but just to sort of highlight that result here. Finally, like I said, everything carries over to multi-time processes. So you have channels. Everything I said kind of readily generalizes in this Pauli in this picture where you have like a tester in the pink and toy matrix of any given unknown channel picture. You can basically write this output probability as trace of E times Cn, which is exactly the quantity that we have been dealing with, right? So I hope it's kind of intuitive to see how this readily generalizes to multi-time quantum processes, although there are things that you have to prove for norms that you have to work with when you talk about multi-time quantum processes, which again I would not have time to go into, but yeah, so all of that kind of generalizes to multi-time processes, and summarily, what we've done is that we've shown that there is a poly-n mistake upper bound, and in fact almost matching lower bounds for Pauli channels, and in fact any combination of any convex combination of known channels, channels with bounded gate complexity, and multi-time processes with the structure above. Then we showed that these things, while the algorithms that we gave are computationally inefficient, can actually not do much better. Also, we showed how a proof technique can give you, shadow tomography of versions of quantum processes, which is Pauli channels in this particular case. And at the end, I would just want to highlight some open questions. Firstly, a natural open question is that what are further classes of quantum channels that admit good mistake bounds? Right. So we gave 3 examples, and I think a very natural question is to find out what are more examples of quantum channels. The setting that we have in online learning is actually for completely adversarial setup, and people might argue that, in the lab, you don't really have a completely adversarial setup. And so, you know some things about where the measurements are coming from or how they're like. And so can we say something about quote unquote benevolent adversaries? So that is, closer to practice. And then, of course, going back to the motivation, can you sort of similarly come up with shared tomography algorithms for further classes of quantum channels? And I think with those three questions, I will make the floor open for further questions about the topic. Thanks.
All right. Thank you very much for a very nice, very informative talk. Yeah, so we have time for maybe a few questions from the audience. Again, if you have a question, you feel free to unmute yourself and speak. Okay, maybe I can start with a quick question. So for this case where you have the multi-time process, right?
Right.
Yeah. So for the channels that gets applied in each of the time step, it has to again come from some known unitaries or from the Pauli channels, right? That's where your result extends in a sort of, I guess, natural way.
So there, the idea is that these Ds could be like, so the tests are in pink, right? The channels that you apply in pink in between after each application of the of n, they're known. They're given to you by the adversary or the adversary.
Yeah. But I mean, I think there's what I'm saying is like there's a restriction, of course, on the n, right?
Of course, exactly.
Yeah. So now my question is, what if I know that for only a few of them, this n is outside the thing that you want? Does your result still extend?
Right. Good question.
Maybe it's not obvious at all, right?
Yeah. I'm going back to the proof. I'll have to think this through. It's not obvious.
I was just wondering, like, if like one of the ends was like all of the ends are Pauli's except for one. Can I already say something in that case? Yeah.
That's a very good question. I'm just thinking if maybe the adversary can exploit this already.
Yeah, maybe he can just really.
Yeah, because you have to take care of the fact that the adversary is completely malevolent. And, yeah, it's an interesting question. I think one would have to think this through.
All right, I will give others an opportunity to ask questions.
Okay, thank you for the very good talk, informative. But I'm curious about the measurement part. Why how to say? You make your measurement large crossing law and n in this figure. For example, the measurement is done for the both law and why is the advantage of doing this? I still do not get it, because according to some broadcasting theory, the law at n is not allowed to exist like this way.
So if I understand the question correctly, you're saying that why are you making measurement on both the reference system and the actual system?
Yes.
Okay. I think that's because we want to give bounds that are a bit more stronger, right? So a measurement that you can sort of entangle between the reference system and the output system and still give guarantees for is something that is stronger than just a measurement that is on either of the systems, right? So what we are giving a guarantee for is a measurement that is could be possibly entangled between the reference and the output systems, and not just a measurement, even the state that is going in as the input.
Okay, so this kind of measurement is it must be entangled to make.
Sure.
Yeah. Okay, I see.
But at the end of the day, you also can you can just not have the reference system, right? You can just what I was saying is that let me just get my pointer out. Yeah, right here. So you can just not have this reference system, right? Have the dimension of the system to be 1.
If it's to be 1, then the input to the channel will be just the same, just 1.
No, just the dimension of the reference system.
Oh, dimension. Okay.
Exactly.
I see. Okay, thank you. My another question is you mentioned about the one-way function and the random state part. What is the relation to that part? I kind of don't get it.
Okay. So there you see that when you talk about this computational hardness result, even if you write this result rigorously, one can just sort of say that this result is while true is kind of too simplistic in the sense that you need an exponential time to even read the input. So forget about learning the entire thing in polynomial time. And so what I was getting at is that we do give hardness guarantees for learning in the case that the input that you're given from the adversary is of polynomial length. And there we embed sort of pseudo-random functions in online learning of these type of functions, such that we can inherit the hardness guarantees for learning pseudo-random functions, and still show that even if the input is poly-sized, even there are instances where you cannot learn the channel efficiently, assuming that that one of the functions exist, and hence pseudo-random functions exist.
Okay. So because you are going to prove the hardness for the lower bound, so you need to incorporate some function that can help you do this.
Exactly. Yeah.
Okay.
Yeah.
Okay. Thank you.
And there the idea is that you have the pseudo-random function, how you implement this in what depth, and there the guarantee kind of and there you can give a guarantee for learning quantum channels with some depth, right? So we give online learning guarantee for learning channels with polynomial depth, and so once you know that at what depth you can implement a pseudo-random function, you can already see that how to sort of encode that sort of structure in the problem that we care about for learning quantum processes with bounded depth.
Okay. I see. Thank you. Yeah, very nice.
Right. Okay. So just wondering if there's anyone else with questions. Okay. Oh, okay. Mincho actually already left, I guess, because he had to go to a different meeting. Yeah. So maybe I can ask. So as you say that, so your scenario is like completely adversarial. but maybe sort of like one can try to sort of reduce what the adversary can do in some sense. So what would be sort of like a natural kind of restriction to the adversary?
Yeah, and I think this is a good question, because this kind of goes to this this point, the second open question towards quote unquote benevolent adversaries, right? In the sense that, okay, what are, you know, a bit more natural assumptions for, you know, helpful adversaries? And there you can say, okay, what about the adversary kind of gives you state measurement pairs from you know, a certain set or a certain class, right? That is already known to both the adversary and the learner. They're adversarial, but you know that they have a particular structure already, and the structure could be anything on the level of the operators, right? So you know, k local, whatever. And so that's one thing. So you know some structure, some sparsity assumptions whenever you write these you know, state measurement pairs in some bases. That is another structure that you can think of. And right, so those two are off the top of my head. Yeah, I think at least those two would be already a good, very good starting point.
Yeah, okay. I guess again, the point is sort of like at least some kind of like common information that's available to both the adversary and the learner will sort of already, I mean, at least if you can sort of motivate why they would both know this, I guess should be fine. Yeah. Or maybe one can really just start with sort of like a physical setting where the learning happens, and then maybe one can try to see what kind of restriction you need. Okay, I'm sort of just trying to think of
what
would be sort of yeah. I understand. Yeah, there's certain kind of structure that already limits how much cheating the adversary can do.
Yes, exactly. I think that's not too unphysical of an assumption, right? Because like you know, in some settings, you like, okay, I'm not an experimentalist, but I can imagine that you know, you would know that you know, in a given setting, what kind of measurements kind of come up often enough, right? And so that's already kind of not too far of an assumption, or too strong of an assumption. And so yeah, I think that's fair. On the other hand, what you said about, you know, where the mistakes happen, you know, like you do have like a total bound for the number of mistakes, but can you kind of give guarantees for like the on the frequency of mistakes, kind of, you know, where did they happen more, where did they happen less, to understand just a bit more about, you know, what is happening about this frequency of mistakes. That will help us. That'd be super cool, actually.
Yeah. Yeah, I mean, but I imagine it would be hard in a fully adversarial scenario. But yeah, maybe with certain structure, one can even determine that which things are like likely to be the mistake.
That is true. I think because I think that will need a bit. That would need new techniques. Because yeah, I think all of these existing techniques kind of work by bounding the total losses. You see, in regret, you have the total loss summed over, and there you would have to kind of be a bit more smart about how you bound things.